Jülich. And today's speaker is the Professor Tim Bode. It is correct pronunciation. It's not so easy.
Though I'm not a professor, but yes.
Great. So anyway, so he will be talking about the adiabatic bottlenecks in quantum annealing and the non-equilibrium dynamics of the Paramagnons. So please start your talk.
Yes, thank you. So I would like to thank the organizers again for inviting me. My talk will have 3 sections, roughly. So we'll speak about our mean field algorithm for combinatorial optimization. And then we'll have a look beyond mean field to the level of Gaussian fluctuations and how that can help us to detect minimal spectral gaps in the annealing schedules. I have one slide on our institute. So we are a relatively new institute, yet founded in 2020 at Forschungszentrum Jülich. For those who don't know it, that's situated right between Aachen and Cologne in Germany. And we are a relatively diverse institute. So we do a lot of quantum control, mostly for superconducting qubits. But we also have a group for mathematical physics and a group for quantum simulation and one for quantum algorithms. And we are still growing, I would say. And our head is Frank Wilhelm Mauch, who you can see here on the right. So what is the motivation for my talk? There is this older paper by Amin and Choi stating that the fundamental problem in adiabatic quantum computing is to relate the formation of G-min, where G-min is the minimal spectral gap, to the structure of the problem that is being solved. And while we are, not, of course, not solving this problem completely, we will at least try to present a method that can help doing this relating of the formation of G-min to the structure of the problem. And on the right here, you can see one example, which is an example instance from the Sherrington-Kirkpatrick problem. So this is a random instance, but sort of one that is very hard by construction. And up here, you see the energy eigenvalues, and one can see here, okay, the gap is basically completely closing. And for the adiabatic theorem, there's another quantity that is important. We will come to that later. That is sort of the coupling induced between the eigenstates by the changing Hamiltonian. And as you can see, right in this area, there's also a peak in this coupling. And so this section here, which is marked in gray for this particular example, is the bottleneck that we will be concerned with. And so why can these spin problems be hard? Well, the one perspective to look at it is via quantum spin glasses. And the paradigmatic model here is the Sherrington-Kirkpatrick model, where we have Gaussian distributed random couplings. And since these can have positive and negative signs, that leads to frustration, as is very well known. And this frustration is what makes the structure of the ground state interesting, but also hard to find. Yeah, and then there's this sort of universal perspective on quantum spin glasses, where we have the temperature on one axis and the magnetic field that we want to anneal on the other axis. And down here, there will be the universal quantum spin glasses, for which the SK model is typically a good example. And then coming down the y-axis here would correspond to classical annealing, where we lower the temperature gradually, while going here on the x-axis, removing annealing the transverse field is the quantum version of this. And of course, there can in principle also be combinations of both. Another perspective on these spin models is combinatorial optimization, where we, for instance, want to solve constraint satisfaction problems. One such example here from so-called maximum 2 satisfiability is given up here. So this is a string of logical clauses, and we want to find the assignment of these x variables such that there's no contradiction in this clause. And I guess this is known to most people here. One can map this, for example, to classical spins, where the logical variables go to classical spin variables. And then one can map this, this literal to such a spin-spin interaction. And then, broadly speaking, the number of violated clauses in this logical statement corresponds to the energy. And naturally, we can do the same in the quantum case. I sort of on purpose switched convention here. So in this case, I assign the zero state with false. One can also do the other convention. It doesn't really matter at the end of the day, and one can find both conventions in the literature. And then, as we can already see here, this again maps to a Hamiltonian of Ising form with spin-spin interaction terms. And then again, the goal is to minimize the energy to find the most optimal solution. And then one can also ask, okay, what is the relation between going basically on this y-axis that I had previously, where we anneal the temperature, versus annealing the magnetic field in the quantum case. And people from our partner Institute for Advanced Simulation, for example, they have also built a mean field algorithm to solve constraint satisfaction problems, which is based on this quite classic paper by Roy Glauber. And so the physics behind that is basically one assumes detailed balance and then constructs a Markov process that updates the spins, and by construction has the equilibrium state as a steady state. And they have shown that this can also perform very well when solving constraint satisfaction problems. Now, the point about doing quantum annealing instead is, of course, that we assume that the probability to get across an energy barrier, so to basically tunnel out of a local minimum, will be proportional to the height of the barrier, instead of being proportional to the square root of the barrier in the classical case. Yeah, so this proportionality here for the quantum case, sorry, the other way around, right? I mixed it up. So the probability should be higher in the quantum case because it's proportional to the square root as opposed to the classical case. And indeed, together with the people from the IIA6, we are currently working on making a comparison between our quantum mean field and this classical mean field, but that's ongoing work. Now I wanted to briefly show my setup for quantum annealing. So I will have a problem Hamiltonian in the standard Ising form, but including a local field, which I denote by AHZ. And then I have the transverse field, and I typically set capital gamma to 1 and use that as a unit. So unless it's explicitly stated otherwise, time will be basically in inverse units of gamma and frequencies in units of gamma. And then the full adiabatic Hamiltonian I'm considering is basically given here. And for the time being, we will assume that S, which is the adiabatic schedule, is just a linear function as shown up here. And then here I again have the SK example from the earlier slide. But now here, down here, we also see the overlap between the instantaneous ground state and the optimal solution state at the end of the schedule, so for S equal 1. And we have in red the fidelity basically that corresponds to this hard example that we see here, whereas in blue we have one corresponding to such a large gap as indicated here by the dashed line. And we can clearly see, so for the hard instance with a very small minimal gap, there's basically a jump from 0 fidelity to almost 1. And this is basically the finite size analog of a first order phase transition. Whereas if there is a large gap, like in this case, there's more like a gradual transition. Okay, I also wanted to mention briefly the quantum approximate optimization algorithm, which is of course related to annealing in a way. So if we assume the exact time evolution as given up here, then we can trotterize that and introduce variational parameters gamma and beta and introduce a QAOA state like this with sort of alternating applications of these unitaries as applied to the initial state. And then in QAOA, we typically want to maximize this. For usually people, the more natural thing is to minimize, right? But then we can just flip the sign in the problem Hamiltonian, and we are back to the same problem. And I'm mentioning this because it's relevant for our mean field algorithm. Exactly. So this has been published last year, and this is so we like this a lot. It's basically an algorithm that will allow you to get sort of an alternative solution for whatever optimization problem you're considering. And if mean field gives you a solution that is lower than what you have by other means from the D-wave machine, for example, well, then you immediately know that the problem is essentially not hard to solve. And this is sort of our motivation for looking at this mean field algorithm, to get a comparison solution for other methods. And the mean field approximation of the adiabatic Hamiltonian is very simple. So the quantum spins are then replaced by basically classical spins, where each spin lives on its own Bloch sphere. And the density matrix can be assumed to factorize in the mean field approximation. And then the classical spin vectors are just defined like this. And each of these classical spin vectors will sit in the effective field that is induced by the interactions with all of the other spins. And one can now work the dynamics out systematically. And here's the analogy to the QAOA. If you sort of consider these variables here in the analog fashion to the QAOA, where you turn them on and off sequentially, then you will end up with a set of linear equations like this. So these are the mean field equations for beta equal 1. So when the problem Hamiltonian is active, when the driver Hamiltonian is active and the problem Hamiltonian is turned off. And on the other hand, you get these two equations when the problem Hamiltonian is active and the driver Hamiltonian is turned off. And this dynamics will conserve the norm, so the vectors stay on the surface of the Bloch sphere as they should. And then the catch here is this can basically be solved analytically. So of course, this matrix VP here will still depend on the magnetization. So this needs to be updated every step. But even so, this allows us to get a very efficient sort of mean field approximation to the annealing dynamics. So we basically steal this sequential application of these matrices from the QAOA, but then we do not optimize over the parameters gamma and beta, but rather we basically pick a standard annealing schedule and discretize it and take these parameters from there. So the idea is we have this algorithm which basically allows for a semi-analytical solution, but then we simulate quantum annealing via mean field in a sense by picking a very slow evolution. And it's really quite simple. So you start from an initial state where the spins point in x direction, and then you pick some final time and a number of steps, and you basically just let it evolve. And then in the end, we obtain a resulting bit string by basically just rounding off whether each spin is in the southern or the northern hemisphere. And this is then what we call our mean field solution. And this can be compared to solutions that you get from other methods simply by explicitly evaluating the energy. We have applied this to two models. One is the SK model. And there's this paper by Farhi where they apply the QAOA to the SK model and claim that it can surpass known other algorithms, such as zero temperature annealing, where you basically just flip spins and accept an update if it improves the energy, if it lowers the energy. And then we have shown basically that already for relatively moderate n, we basically in turn surpass this with our mean field algorithm. And we can also show that we reproduce a number of known results from the literature. For instance, that the energy is distributed in this way, where the red dashed line is a so-called Gumbel distribution. And we can also show that the tails of this distribution go down quite rapidly. And so basically we can show that for the SK model, one should not expect the QAOA to really deliver an advantage here. We have also looked at the partition problem, which is the problem of separating numbers into two groups such that the difference of the sum of either group is as close as possible to zero. The cost function is given up here. And then by squaring that cost function, this can again be brought to Ising form and then addressed with quantum annealing or the QAOA or our mean field algorithm. And we get this very nice, almost analytic scaling for the tails of the distribution again. And also we can show that if we compare directly to QAOA, which is shown here, mean field systematically has a better scaling. Yeah, so for this problem, since we have squared the cost function initially, the natural thing is to look at the instance, at the disorder average of the square root of the energy. And as you can see here, mean field has a scaling n to the minus omega with a given exponent, and the QAOA has a similar form, but with a much worse exponent. And this means that, again, for this problem, mean field performs quite well, and this is a problem for the QAOA. I would like to point out that the software for this is basically online on our GitHub repository of our institute. And so you can basically just use it and play around with it. So this is a Julia code, but there's also a Python code available on our institute GitHub page. Yeah, so this was basically the first part of my talk, which was just a summary of this mean field algorithm. And on this, we now want to build by going beyond mean field and considering the Gaussian fluctuations around this mean field, essentially. And this preprint has appeared recently. So the stereographic projection is quite well known, I guess, and it can also be applied here to map the coordinates of each spin into the complex plane. And this allows to define a path integral for the spin dynamics. And under this mapping, essentially, the north pole will go to 0 and the south pole will go to infinity, or vice versa, depending on which point we pick to do the projection from. Yeah, and the equator will basically go to the unit circle in the complex plane. And the catch is, of course, the measure for this complex coordinate that we get from the Bloch coordinates is not flat in general. And so one can't really do much with this path integral. However, one can show that in the Gaussian approximation, we again get like a flat standard measure. And so we can define a Gaussian path integral that is well behaved and with which we can work. And these matrices A and B, they depend on the mean field coordinates. And so they basically, they change as we move along the adiabatic schedule, and they define the dynamics of the fluctuations. And one little detail, so we found that it's important to pick the projection point for the stereographic projection independence of the solution bit string. Yeah, so if we know that the mean field solution will end up close to the north pole or close to the south pole, then accordingly we pick the opposing pole to do the projection from, such that the coordinates at the end of the trajectory will be close to 0 and not blow up to infinity. And the thing is, this is basically a bosonic path integral. So once we have this path integral, we can also essentially just drop it and go back to the operator formalism. And if we do that, we end up with a quadratic Hamiltonian that has anomalous terms, like in BCS theory, if you will, but this is just a formal analogy, of course. Yeah, and this Hamiltonian essentially defines bosonic quasi-particles, which we will call Paramagnons in this talk. And then what we would like to do is to study the full non-equilibrium dynamics of these quasi-particles. And this can be done via the so-called Schwinger-Keldysh formalism, where we introduce the so-called greater and lesser green functions that are defined in this way. This formal definition is less intuitive, but there's a nice way to think about this. So at equal times, t equal t prime, the greater green function will essentially encode the number of quasi-particles. Yeah? So the n here is the number of Paramagnons. And then in the greater green function from the commutator, you get a +1, which is basically the vacuum fluctuations. And the lesser green function is basically just directly the Paramagnon number. And then, of course, you have the Gij, the off-diagonals, which basically encode correlations between those Paramagnons. And then, essentially, it's a quite standard problem of the equation of motion theory for these green functions. You can then set up the equations of motion. And again, in this Hamiltonian matrix, these fields A and B will show up that we already had here in the path integral. And again, A and B depend on the mean field coordinates. So basically, one has to solve the mean field dynamics once, and then all of the coordinates are known. And then with that knowledge, one can also solve the dynamics of the fluctuations. And just to illustrate this a little more, these functions are generally defined for 2 times, right? So t and t prime are the arguments. So they live on this 2 times square. And typically one would have to solve the dynamics also in 2 dimensions. However, for the Gaussian case, this simplifies. One gets away with just solving the dynamics here on this diagonal. So on this diagonal, t is equal to t prime. And this, if you wish, is the physical forward time, the actual non-equilibrium time along which the system changes. And then decoupled from this, in the Gaussian case, is this tau dynamics, where tau is t minus t prime, so the relative time. And the Fourier transform of this tau is essentially the frequency that you would see in a spectral function. And so basically, you can solve the complete dynamics here by just evolving forward in time. And then for each point in time, you can take an orthogonal slice and also do the dynamics in this direction to obtain the spectral function. Right, and so now we are moving back to this illustrative example that we have already seen a number of times. So here again are the energy eigenvalues, and here is the coupling between the eigenstates induced by the changing Hamiltonian. Yeah, so this is shown here. One can look at this this quantity, which is basically the relevant quantity for the adiabatic theorem. Yeah, so this thing should be much this thing divided by the final time should be much smaller than 1 to be safely in the adiabatic regime. And for this example instance, this peak, this quantity is about 5 times 10 to the 4, so very large. And so for this example, essentially, we can assume that the final time is so large that right now, I don't think one could realistically solve this on the D-wave machine, for example. Yes, and we will also denote the location here where the fidelity jumps and where the minimal gap is located by S prime, which is basically the bottleneck point that we are concerned with. And now, again, we are still looking at this same example. We can also see what the mean field trajectories will do. And it turns out that there are certain spins which are much less localized than others. Yeah, so here we have the Z component, which basically indicates the localization of the spins on the computational basis. And you can see that here there's one spin marked in red that localizes a lot later than the other spins. These spins here also localize later than those, but let us just focus on this one, which is the most frustrated spin, so to speak. And then we can also explicitly look at the effective magnetization. Yeah, so this is this quantity, this effective field, which is the local field plus the mean field seen by this spin as induced by all of the other spins. And we can see that basically this magnetization stays zero during the entire time. And so what this means is like that for this particular spin, the interactions, they just essentially sum to zero, and the spin is sitting there and not doing much. And the interesting catch will come when we look at the fluctuations for this spin. Yeah, so this is to introduce sort of this concept that there will be single or also multiple spins that will be very frustrated and localize much later. And typically there's a connection between the localization and the minimal gap, or the bottleneck, if you wish. Exactly. And so now we can, like I said, we can look at the Paramagnons. So I've been telling you that the lesser function at equal time is essentially the Paramagnon number. And we can look at that for all of these spins. And we see indeed that if we look at the fluctuations of this maximally frustrated spin that we had identified earlier, we see that this one is fluctuating most strongly, and it does so right around the location where the adiabatic bottleneck is. And so this is an interesting observation. And so this alone would this fluctuation peak alone would basically already give us an indication of where the bottleneck is. But then I sort of semi-empirically found that if I construct a quantity which I call the localization susceptibility, which is basically the product of this local order parameter Qi, which I had introduced earlier, which is just the square of the Z component. And then the well-known Edwards-Anderson parameter ends up being the sum over these Qi's. And so if I multiply this together with essentially the Paramagnon number here, so this additional factor in front is basically just a scaling factor on the complex coordinate plane. This is not really relevant for us now, it's a technical detail. But essentially this local order parameter multiplied with the fluctuations, this turns out to give basically a perfect agreement in this case between the peak of this quantity chi and the peak of the G1, which is this quantity from the adiabatic theorem. And like I said, this peak is quite high in this case. And if we then look in this inset here also at the annealing dynamics, we indeed see that we have to go to relatively large final times. So we have to do a very slow annealing dynamics to get a substantial fraction of probability on the actual ground state. 2 to the 13 is 8K, right? So here basically the ground state is not visible, and the dynamics converges on the first excited state essentially. Okay, so this has simply been an illustration. What one can then do is to look at disorder average statistics. And what I essentially did is I for different values of n shown here, I just generated a lot of random instances and then separated them into two data sets. One where the gap is very small, smaller than 10 to the minus 2 is just some cutoff I ended up choosing. And then I also have an alternative data set where I retained instances that have very large gaps. So basically an easy data set for comparison. And I should say that both the easy, I think on our repository right now, I only have the hard instances. So these with the small gaps. So these are freely available. So in case you ever need hard instances to test some of your methods, you can just take them from there essentially. And this example here with this peak is not even the hardest one. So I have for all values of n, there are instances that are even harder than this. And okay, yeah, naturally, so for n equal 18, it's already quite expensive to get the exact spectrum. I essentially use the RPARC package, which is like the Langtos method or similar things where you just get the eigenvalues with the largest magnitude. And this allows you to relatively cheaply get a bunch of lowest eigenvalues to compare to. But naturally, this is much more expensive than for smaller n. And so the ensemble size naturally goes down. At the same time, we sort of expect that for larger n, there will be some self-averaging. So one should also be fine with not having as many instances in that case. And then essentially what I did, I calculated this, I identified the maximally frustrated spin for each instance simply by sort of picking the spin with the lowest local order parameter as defined here. And then I calculate this quantity for each instance in the disorder ensemble. And then I rescale everything with the true known S star location of the bottleneck. So for each instance separately. Then I shift all of the fluctuations according to this S star. And then only afterwards I do the average. And so by this construction, basically, if the peak comes to rest around 0 on average, so this basically confirms that indeed also for larger ensembles, on average, there will be an alignment as seen here. Of course, it doesn't always work as well as in this case. So the agreement is not always perfect. But on average, we can see the peak comes out relatively close to S minus S prime equal to 0. Not for the smaller system size, it doesn't work as well. This is also expected. And I should say, so this is all for the SK model, but we also have started to apply this to maximum 2 satisfiability, for example. And there it also seems to work. And we are basically working on applying this to a larger set of combinatorial optimization problems. Yes, so this brings me to the final part of my talk. Should we stop for questions maybe, or should I just go on?
Please proceed your presentation.
Okay.
Do we talk? Yes.
Yes. So like I just said, we are considering applying this method to other problems. We are also extending our mean field algorithm sort of beyond the two-body interaction restriction. So right now we can basically just solve problems like max 2-sat or the SK model. But I have a student working on the generalization to basically arbitrary k literals. So then we could address max k-sat, or my student is also looking at max k XOR. So we are working on all of that. And so far also getting encouraging results. But here I want to flash basically an idea that a master student of mine is working on. So there's this paper with the geometric approach to optimal schedules. And this is sort of very nice for everyone who has studied GR in the past, because it's essentially possible to take this quantity from the adiabatic theorem and define a metric tensor with this. And then we can stick this metric tensor into a standard Lagrangian as would be so the path lengths as one would define it in GR with the standard Christoffel symbols. And then by solving the geodesic equation, one can essentially get the optimal schedule that corresponds to, well, the adiabatic bottleneck as encoded in the adiabatic theorem. And in the one parameter case, well, this becomes very simple. So it's just this, this differential equation here with quite straightforward Christoffel symbols. One should say, however, it's not completely trivial to solve this, because this is not Newton's equation in the standard sense, because it's not an initial value problem, but it's a second order boundary value problem, which is the technical term, because of course you have this final condition. Yeah, so the schedule. Oh yeah, I didn't mention this. So I'm switching here from this notation S of t basically to x of s, and in the linear case, x of s is simply s, right? But anyway, so of course the schedule should obey some boundary conditions, which essentially is given here. X of 0 should be 0 and x of 1 should be 1, and this turns this into a boundary value problem as opposed to an initial value problem. But then there are established methods like the shooting method for solving this. And so now, of course, the semi-obvious idea is that we could try to replace this metric as defined here, essentially by our Paramagnons, basically. And so Chris Ramesh is a master student of mine. He's been working on this. So I stole a couple of plots from him to give an outlook. Here, essentially, we have another example of the SK model. Again, the energy levels, and down here we again see this quantity G as applied to the first excited state. And so this again marks the this S prime location, which is the adiabatic bottleneck. And we can again look at the Z components of the mean field dynamics, and indeed we find, okay, there is again two spins essentially that stay very frustrated basically right up to the adiabatic bottleneck, and then they localize quickly. And then we can again look at the fluctuations for these two spins, and indeed it turns out that there is quite a good agreement between the peak of the Paramagnon number and the adiabatic bottleneck. And then yes, so then we can basically use this this peak down here as our metric for the geodesic equation to obtain a schedule. And then basically there is sort of one tuning parameter in there, basically just the absolute scale of the height of this peak. So by rescaling, by normalizing this first and then rescaling it with some constant, we can essentially control how curved this schedule is going to be. And so if we have a lower peak, then is not much curvature here, while if we make it larger, then we get these very curved schedules that are basically very shallow around the S star adiabatic bottleneck location. And so here, of course, you have to think about it on the y-axis. So basically, this dashed line, when we imagine it to lie on the y-axis, then we can see that the schedule basically slows down right around the bottleneck. And then we can first of all look at the fidelities between the final state and the instantaneous state, and also the first excited state. And if we do that for a linear schedule, well, then we see that the overlap with the solution state, which is given in blue here, this goes up at some point, but it goes to about 0.5 for this final time. And I should say, so according to my understanding, if I put the initial transverse field to 1, and then I translate the parameters from the D-wave machine, then the D-wave right now should be able to do dimensionless times of 1,000 roughly. So if I look at their latest papers, this is what I gather. I'm not sure if this is quite accurate, but more or less. And then again, of course, we can throw out the linear schedule and plug in our we call this adaptive schedule. So our curved schedule that we are deriving via the geodesic equation from the Paramagnons. And then we see that indeed this gives an improvement in the overlap with the two solution. And I should say this is not the best example. So we have other examples that are much harder. So where this peak is much higher, and there typically the overlap of the linear schedule is basically negligible, while we typically are able to get some small but finite probability from our method. Yes, and this is actually, I'm already at the end, so I'm happy to take questions.
Okay, thank you very much. Very interesting talk. So now, okay, yes. So any question or comment? So if you have comment, please switch on your microphone and yes, Viv, please, yes.
Hello,
Hi.
An excellent talk. Thank you very much. I'm in a hotel room, so the quality is not very good here, but hopefully you can hear me.
Yeah, I can hear you.
Okay, good. So you've been having really fun with this stuff. You've done a lot more than when I last talked to you. This is great.
Yeah, right. Yeah, it's been a year almost, right? So, but yes.
So I wasn't picking up completely from the details in the talk. It's great analysis to understand what's going on. But which things give you a method that doesn't cheat? And which of them are for understanding what's going on? Because if you know the position of the gap, of course you can do a great,
Oh yeah, okay.
Schedule, right. But are you allowed to know that, right?
I probably should have stressed this more. So whenever I plot this G1, for example, then of course I know the exact spectrum, right? But I only do that for comparison. Yeah. And the catch is that we can calculate these Paramagnons relatively cheaply. So this is like an ODE system of size 2n, I think. So you have 2n ODEs, right? It should be. So anyway, it's like polynomial in n, let's say.
Okay. Yeah.
And there is so one has to see how. So for the hard instances, it's typically more expensive to solve these ODEs, but you can still do it like in sort of polynomial time, I would say. And so, yes, so this is basically a semi-classical method that supposedly one should be able to do for large n, and that should give one an idea where the adiabatic bottleneck is without solving for the exact spectrum. Yes, so the schedules I have derived here at the end. So this is from the Paramagnons here, right? So I'm using this curve, which is basically a classical quantity. And from that, I'm doing the schedule. So I'm not using any exact information that I would not be able to get for large n. So in principle, this should work.
Cool. Okay, so now we want to know how sensitive it is to the position of the plateau that you have to put in there, right? So how accurately do you need to know, does the Paramagnon calculation give it to you accurately enough?
So,
I mean, the answer probably is yes for many problems, but it's like how to show that.
Yeah, exactly. So what we are considering at the moment is basically just doing a disorder average over the ground state improvement that we get relative to the linear schedule. Yeah, so we would do the linear schedule quantum annealing and then replace the linear schedule by our curved schedule and see how much better we can get. And as you know, there's
Okay.
this data set from this Croissant paper, right? So
Yes.
we are about to evaluate this stuff finally, and we have done that for a couple of examples, and it looks like we get very large improvements sometimes.
Okay, cool. Yes, because, and I think I think Paya's, like all of the other related data that Paya generated for working with that are also online at Durham, probably.
Yeah, we
So
also have those.
the comparison ones.
The thing is actually, typical data sets don't have a lot of hard instances for let's say formats2 at least,
exactly.
for the SK problem. So for my SK data set, I had really to generate a lot of random instances to retain like a non-trivial number of very hard ones. But we also know that this changes once you go up in K, in the K-sat sense, right? So for 3-sat and so on, it's more like most of the problems are very hard. So making that shift should help there. Yes, and in terms of how, I mean, this plot somehow suggests that at least for the SK model, the agreement between the Paramagnon peak and the actual mini gap is quite decent. Yes, but we are still sort of working on quantifying how well that works. So by just doing the comparison when doing the annealing, yes.
Yeah. So it's like what's your margin of error before you lose that you lose the improvement, right?
Yes. And there's also this question of sometimes it simply helps to not use a linear schedule, but to introduce some sort of excitation, because sometimes this will like bring you into the excited state early on, and then sometimes you fall back down, and then you can also end up in the ground state. So one has to be careful to sort of control for this effect, which is not what we want, but we are also aware of that basically. What I forgot mentioning here is, in fact, that the instances I'm using here in this hard data set are all instances where mean field fails to find the true solution, right? Because this is important, obviously. If mean field gives me the true solution, then I'm basically done, right? Then I don't need to need to do quantum annealing. And so I basically discarded all of those and then retained a data set where mean field fails, and even so, the Paramagnons seem to have some indicative power for the bottlenecks. Yeah.
Cool. Excellent. Thank you. I'm hogging the questions. We should give other people a turn.
Okay. Thanks. So Paul, please. Yes.
Yeah, hi Tim. Very nice talk, which I understood some at least. So you clearly convincingly demonstrated that this Paramagnon peak gives you an estimation of the value of S at which you have your minimum gap. That seems good. Does it give you any information about the magnitude of that gap as well? Is that somehow in there or not?
Right. I actually have not checked for that. It's a good question. Just my experience from seeing a lot of data is that it does not. But right now I cannot say, actually. It's another question we should investigate. For me, it was somehow always clear that somehow the location is the more interesting parameter, in the sense that really hard problems will probably not be solvable anyway, at least not exactly, right? And so we just want to be as good as it can get, and then it's more relevant to know where we should slow down as opposed to how much, right? Because you can always just try to make it even slower at the right location and see how you improve.
When you feed this information into your optimized schedules,
yes, I mean, yeah, but there we can basically control the curvature just by some fudge parameter, right? And so and then you can basically just do trial and error, assuming you really have a hard problem where you really want to know the solution or get a good solution. Then it doesn't really matter how hard it is, because presumably, I mean, I've seen peaks that are like 10 to the 10, even for small system sizes. And practically those are basically infinitely hard. And then it's just a question of improving, I would say.
Understood. Fine. Thank you very much. Thank you.
So, okay, so time is already up. So let's thanks to the speaker again. So very interesting. So thank you very much.
Thank you.
Thank you.
Chen. Bye.